Okay, so here's a more detailed explanation of a demonstration that I did a couple of lectures ago. I have a stream of water here, and each individual water molecule has a dipole moment associated with it. Recall that the dipole moment is a description of the polarization of a water molecule. Okay, and then what I'm going to do is I'm going to place these water molecules here in the presence of an external electric field. So I'm going to go ahead and take my plastic rod here, and I'm going to charge it by friction, thereby giving it a positive charge. And then when I do, you see that there's a force of attraction that's exerted upon the water molecules towards the positive charge. So what we're doing here is we're taking a dipole, in this case the dipole moment associated with water molecules, and we're placing it in the presence of what is called an external electric field. So not the electric field due to the dipoles themselves, but the electric field that is caused by this plastic rod when it has a positive charge. Okay, now watch what happens when I take the glass rod and give it a negative charge. And then once again, we take the dipoles associated with the water molecules and place it in the presence of the external electric field. And then notice once again that you have right here a force of attraction that's being exerted upon the individual water molecules yet again. Specifically, what's happening in this demonstration is that there is a torque that is being exerted upon each individual dipole moment associated with each individual water molecule when we place those dipoles in the presence of an external electric field. Okay, now I'm going to give you a brief qualitative description of what is happening here in these simple demonstrations on the board. Bear with me while I move my phone in order to do so. Okay, so moving my phone. Okay, like so. Sorry, I have to make my phone a little bit more stable. Okay, there we go. Okay, so just a qualitative description. Placing a dipole in the presence of an external electric field. So once again, not the electric field due to the dipole, but the electric field that is caused by something else. In this case, my plastic rod, positively charged, and then secondly, the glass rod, negatively charged. Okay, let's see what happens with the positive charge. Okay, so let's say right here is my positively charged plastic rod. Just for simplicity, it's kind of facing out at us like this. And then we would have, I'll just draw them here up to the right-hand side, some electric field lines like so. Okay, so here's my external electric field E, and then I have my stream of water molecules. So right here is an individual dipole moment vector associated with one of the water molecules. Recall that that's referred to as P. And here's the negative side, and here's the positive side. And now let's just think of it in terms of forces. So for example, there's going to be a force of attraction exerted upon the negative side of the dipole due to this positive charge. There's going to be a force of repulsion that is going to be exerted on this positive side of the dipole due to this positive charge. So that's ultimately going to cause then a torque to the dipole like so, but then because this force of attraction here is greater than the force of repulsion here, basically the dipole is going to do something like this towards the positive charge. It actually doesn't matter in which direction I orient the dipole moment vector here in black with respect to this external electric field. For example, so now let me go ahead and take the dipole. Let me redraw this. Now let me take the dipole and say place it like this. So here's the positive side, here's the negative side. So then therefore there's going to be a force of repulsion exerted upon the positive side of the dipole, force of attraction on the negative side of the dipole. And then therefore the dipole is going to begin to torque, but then as it does, it gets attracted back towards the positive side, or the positive charge rather, like so, because of the non-uniform aspect of this electric field. So as it torques like this, then this side here is closer to the positive charge than this side is. So then therefore you get a stronger force of attraction in that direction, like so. The exact same thing is going to happen with the glass rod. Okay, so here's the negatively charged glass rod, and then we have its electric field lines looking something like this. And then let's say that we take one of the dipole moments associated with a water molecule and we draw it like that. So here's the positive side, here's the negative side. So the negative side is going to get repelled by the negative charge, the positive side is going to get attracted, and then it's ultimately going to do something like this. And then once again, ultimately a force of attraction is exerted upon the dipole moment, and it gets attracted then to the negatively charged glass rod. This is due to the non-uniform aspect here of this external electric field. And then lastly, take the water molecule and orient it a little bit differently. Say like so, negative side, positive side. So the way that I have it drawn in this case is that we're going to have a strong force of attraction here, a weaker force of repulsion on this side, and basically it's going to do something like this, ultimately get attracted towards the glass rod. So this is ultimately why you see the same thing in both of the demonstrations that I did. It doesn't matter if I use the positively charged plastic rod or the negatively charged glass rod. Ultimately, you're going to see the stream of water get attracted to the charged object.